Hello everyone and welcome back. In today's video, we are going to be exploring the fascinating world of neural networks by implementing Feedforward Neural Network model using MNIST Dataset. Before we dive into the coding part, let's quickly understand what exactly we are dealing with. With MNIST Dataset, for those who don't know, it's a collection of handwritten digits ranging from 0 to 9. So as you can see here, we have handwriting digits from 0 to 9. Okay. Our goal for today is to train a feedforward neural network model to accurately classify these handwriting digits. So think about it as in we are teaching our computer or we are training our computer to learn or recognize handwriting numbers just like human do. Now let's talk about the architecture. With a feedforward neural network, it consists of an input layer, a hidden layer, which could be one or more, and also an output layer. And each layer consists of multiple neurons, and each neuron is connected to all the neurons in the subsequent layer. So as you can see here, when we take the input layer, a neuron in the input layer is connected to all the neurons in the hidden layer, right? If you want much or deeper understanding to architecture, then kindly check our previous video where we actually dive deeper into them. And once you are done, you can join us and let's get started. Alright, so the first thing is to import the necessary or required libraries. We are going to be using TensorFlow, sequential models, dense layer, pyplot, numpy, and image. Okay, so I'm just going to run this, and the next thing is to load our dataset. So I'm going to create a variable which is MNIST, and then I'm going to use TensorFlow.keras dot datasets dot MNIST. Okay, and then down here I'm going to call my MNIST dot load underscore data. Okay, and then let's run it. Great. Yeah, so as you can see here, we have the first array, the second array, the third array, and the fourth array. Okay, so the first one is the input for the training data. Okay, and then followed by the output for the training data, and then the next one is the input for the testing data, followed by the output for the testing data. So we are going to store this in a variable, and I'm just going to do that by saying x train, so x underscore train, and then y train. Okay, and the next one is x test. Okay, underscore, so y underscore x test. Okay, so we are going to store those arrays in these variables: x train, y train, x test, and y test. Okay, so I'm now going to run this, and once you're done, we can take a look at some of the inputs. So when we take the x train, look at the first value or the first variable, we have pixels right here. Okay, so we have an array of pixels, and it ranges from 0 to 255, right? We can actually get the values as well. So um with x train, so with y train, when you pass in this, okay, so what you are seeing here is the pixels for 5, right? And we can actually visualize it by running or plotting it using the pyplot. Okay, so pyplot.ms show, we are just going to pass in our x train. Okay, let's run it. Great, so the picture we are having here is 5, right? That is basically what we had as an output, right? Yeah, so that is it. And then the next one is to normalize the pixel values. So earlier on, as I said, it ranges from 0 to 255, which is the largest. Okay, so we have to now scratch the digits between 0 and 1. Okay, and we can do that by just dividing all the pixel values by the maximum, the highest number, which is 255. So I'm just going to call x train and then x test. Okay, and then I'm going to divide all of them by 255. 255. divide this one 2 by 255. Okay, so now let's run it. Oops, what's wrong? Oh, sorry, my bad. Okay, so now let's run it, and we can visualize it again. So we can take a look at it just for the first one. Good. So when you scroll down, as you can see here, we've now squashed the values between 0 and then 1, right? Now the next thing is to flatten our image. Okay, currently is the shape for our variable is, let me see. Okay, so the shape is 28 by 28. Okay, we have to flatten it into a 1D array. Okay, so that we can feed all of it into the input layer. All right, so let's quickly do that by typing xtrain and then xtest. Okay, and then sorry, with the xtrain is going to be xtrain dot shape. So we have to reshape it. So reshape. Okay, then we are going to give two brackets and then xtrain again dot shape. We are going to pass in. So we are trying to get only this. Okay, and then followed by -1. Okay, and then the next thing is to do same for xtest. So I'm just going to copy all of this down here, and I'm just going to do xtest. Then let me copy this and paste it right here. Okay, let me do same for here. Okay, so now hopefully we don't get any error. Let's run it. Good. So let's take a look at the xtrain again. So now let's see. Okay, we just have a single array consists of all the pixel values, right? So now we can now feed all these values to our inputs. Okay, let's look at the shape, right? Okay, so now we are having 784. Okay, so which means we are going to feed all the 784 to our input layer. Okay, which means we are going to have 784 neurons in the input layer. All right, so once we are done with that, we can now define the architecture. Okay, so I intend to use a deep neural network architecture. Okay, so I'm going to have two hidden layers. Okay, so let's start by creating a model. So using a sequential. Okay, you're going to first create a dense layer. Okay, so 64 neurons. Okay, which is our hidden layer. So 64 neurons, and then we have an activation function. You're going to use relu. Okay, and then our input shape, which is our input layer, is going to have 784 neurons there. Okay, and it has to be inside brackets. Okay, and then add a comma there, else you get an error. So the next one is another dense layer, which is the next hidden layer. It's also a dense layer with 32 neurons. An activation function, we are going to use the relu. Okay, so let me copy it. I'm going to paste it right here. Then the last one, which is the output, is going to be a dense layer with 10 neurons. Okay, and then followed by an activation function. We are going to use softmax. So let me finish and then explain it to you. Softmax. Okay, great. So yeah, so with the activation function, I won't dive much deeper into it because I have a separate video on that. You can check it out. But for clarification purpose, relu, what relu actually does is it takes an input, okay, and it checks if the input is greater than 0, then it or is 0 and above. It just gives the output as the same as the input, okay. So when you pass in 10, it gives you 10, but when it's negative, it gives you 0. Okay, so it makes sure the model don't give out an output of negative value. Okay, and then with a softmax, what it actually does is it squashes the value between the range of 0 and 1. But in this case, it uses probability. Okay. And as you can see here, we have 10 neurons. Okay. So yeah, that is it. We have our 10 neurons here. And we are using softmax. So which means the values or the output for these neurons, when you sum all of them, they are supposed to sum up to 1. Okay. So that's why the softmax uses probability. So with these neurons, the one with the highest probability or with the one with the highest value is going to be the predicted digit. Okay. So with that being said, we can now run this. Oops. Okay, let me check. I think there is supposed to be a comma here and then a comma there. So now let me run it again. Great. So the next thing is to compile, and then we are going to compile our model by calling model.compile. Okay. And inside it, you are going to use an optimizer and then a loss. Okay. So the optimizer, I'm going to be using is Adam. Okay. And then the loss I'm going to be using is the sparse categorical entropy, cross-entropy. Sorry. So I'm just going to paste that one also here, and then the next one is going to be the metrics you are monitoring. Okay, so the metrics you are monitoring is supposed to be the accuracy. Okay, so great. So hopefully you don't get any error. Okay, so we are using Abdam optimizer, and then the loss is the sparse categorical cross entropy. Okay, and then the metrics we are monitoring is the accuracy matrix. Okay, so I'm just going to run this, and then the next thing is to train our model. So I'm just going to call model.fit. Okay, and then we are going to pass in our x train and then our y train, and then followed by epoch. Okay, so okay, so the epoch is the number of times you want to train the model with the training data set. Okay, and then we are going to pass in the batch size. Oops. So with the batch size, what is happening is going to be 32. Okay, and our validation split is going to be 0.2. Okay, good. So with the batch size is the number of data points we want to feed at a time. Okay, during the training. Okay, and our validation check, we are trying to use 20% to validate our data set. Okay, so I'm just going to train our model. Okay, so as you can see, with the first training, which is the first epoch, training is ongoing. Okay, and once it's done with the first epoch, it will start with the second one. It's going to do that until the 10th one. Okay, all right, so our model is done training, and let me scroll down for us to see. So oops. Okay, so as you can see, our model is done, and for every epoch you could see the accuracy, right? And then the next thing is to evaluate our model. Okay, so we are now going to check the performance of our model. So we are going to evaluate by using the model dot evaluate. Okay, so evaluate, and then I'm just going to pass in the x test and then the y test. Okay, and I'm going to store them in the test underscore loss and then the test or the accuracy. Okay, great. So I'm just going to run this, and once you are done, we can now print. So I'm just going to use say the accuracy. So our testing data accuracy. Okay, yes, accuracy. Okay, so let me copy that and let's paste it right here. Okay. So with our testing data, we had an accuracy of 0.969. Okay, so it's almost like 0.97, which is 97. Okay, so that is what we had for our last epoch. Okay, so you can actually change the epoch and then the batch size to fine tune it and then get the best out of it, the model. Okay, so we've been able to implement a feed for neural network. Okay, so let me just a quick recap. What we actually did was we had our data set, right? And then we normalize our data set and then flatten it to get a 1D array. Okay, so now feed all the 1D array, which is all the data points, to our input layer. And our input layer had a neuron of 784. Okay, and we had two hidden layers. The first one had a neurons of 64, the next one had a neurons of 32. Okay, and all of them use ReLU activation function. Okay, and then followed by our dense layer, which is the output. Okay, and that one we had 10 neurons, and each neuron is supposed to give an output of one digit. Okay, so the first one is going to give an output for the 0, 1, 2, so on. Okay, and the activation function we used was softmax because we want it in terms of probability. Okay, so the output for all of them is going to sum up to 1. Okay, but the one with the highest value is the predicted digit. So we've been able to implement it. I hope you really enjoyed this video. If you did, kindly click on the subscribe button, like this video, share with friends, and see you in the next one.